After that last discussion, I'm going to start off by providing one warning about using the cloud. It only works when you have internet access. So fortunately, I put this on PDF before we started, but some of the slides are a little ugly as a result. I apologize for that in advance, and next time I'll try to do this or actually have Google presentations available with internet access. So this is going to go pretty quick. I think I have about as many slides as I do minutes, and as a result of that, we're going to move through them fairly quickly. I'll try to save a little bit of time for questions at the end, and I'll try to do something like put my clock in front of me to sort of keep track of time. All right, so let me move this further away. No, really, I want to go to the next slide. We're going to wait 1 second. So just by way of introduction, that was mostly covered already, but I manage a team of much smarter than me engineers in New York for Google. Most of my team is focused on managing some of our shared storage infrastructure, and that's the storage that other services within Google use. So if, you know, a good example of this that I use later on in the slides is if you were a service like Google Maps and you have all these map tiles, or Google Earth and you have all this imagery that you want to display, that has to be stored somewhere, and hopefully this is going to work. And the place it is stored is on the pool of shared storage that I'll be talking about momentarily as soon as my computer starts to work. We do this as part of what's called the Site Reliability Engineering team at Google. Apparently it does not include laptop reliability engineering, otherwise you would already see the next slide. But the Site Reliability Engineering team at Google is focused on making sure, basically the bottom line is to make sure that various elements of the Google website stay up and running. And we do this by, you know, focusing on performance, reliability, scalability of our infrastructure, as well as the software. We're the people that actually run the production infrastructure at Google. And as a result of that, all right, we may have to do this really get away. As a result of being the people that run the production infrastructure at Google, we are the folks that get to really deal with the sort of issues of scale at Google, which I'll cover a bit in today's presentation. I'm going to try this one more time, and then I'm going to move on in the ugly way. Slideshow again. Hey, look at that. Okay, so I've already talked about this slide. That's who I am, what we do. The one thing I do want to mention is that one of the key things that our internal storage supports is App Engine and Google Storage for Developers, which are the cloud technologies that Google currently supports that we sort of alluded to in the previous session. So I'm going to start off by talking about some of the building blocks that we use at Google that will eventually trickle down into some more specific discussion about the shared storage infrastructure. But starting with, you know, here's Google, or at least here's what Google looked like quite a number of years ago when it was Larry and Sergey running it out of a lab at Stanford. All fit on these computers. It's much bigger these days. But one of the things I wanted to address first is how Google uses open source. This will be sort of the start of my presentation, and we'll get to some more of it at the end with a little bit less related to open source stuff in the middle. But the most important way that I think that we use open source is infrastructure at Google, starting at the very base. All of our machines run on Linux kernel. We use tons of Apache project tools, management tools like SSH, and then obviously the languages that we use, you know, Python, C++, et cetera, and all those compilers are all based all use open source. And then most of our engineers run Linux on their machines, with the exception of a handful of either Mac or Windows developers who run Mac or Windows for obvious reasons. But the vast majority of engineers run Linux in their development environment, and many people throughout the company run Linux as their desktops as well. And then finally, there's obviously tons of glue in terms of open source libraries and other software that we use in order to make various bits of Google work. There's no reason to reinvent the wheel when there's excellent open source options already out there. So there's tons of that throughout. So we'll get to some more specifics of this later on, but I wanted to sort of introduce this to provide some context around some of the discussion that's going to follow. So starting with sort of the question of what is Google from an infrastructure perspective in particular, it's a lot of interesting stuff that you probably wouldn't expect if you haven't already learned this about Google. Almost all of the hardware is stuff that we put together, starting with in-house rack design. We have people who care about all sorts of stuff that you would never even think, things like airflow and the most efficient ways to make things cool, to make hardware cooled and so on. Energy use is a huge topic. But underlying all that is basically really cheap hardware, low end, often consumer grade infrastructure. We throw in the biggest hard drives that we can find. We get ideally, some very high-speed networking gear, but the CPUs and the memory are often incredibly cheap stuff. And it's a mixture of Linux plus a bunch of in-house software that we run on top of that. So looking at storage in particular, this is sort of a view of the storage hierarchy, starting with what one server looks like, right? We have a bunch of cores up at the top, or processors. They have some L2 cache, depending on the layout. There may be a couple of cores on a single chip, which will have tighter integration than cores that are on separate chips. Similarly, then you've got some L2 cache that's linked together, tied to local DRAM. So a typical server might look like you might have 16 gigs of RAM. You can access that in something like 100 nanoseconds. You can get 20 gigabytes a second of throughput on that. Then you've got some disk that you can fall through to if you need to. A lot more of that, obviously, 2 terabytes, or sometimes more. They're starting to talk about 3 terabyte drives. That you can get to much more slowly, 10 milliseconds for a random access seek probably, and you only get 200 megabytes a second. So already going to local disk, you're losing orders of magnitude of speed and throughput, of latency and throughput. Those servers are then aggregated together on a rack. Those racks have switches that link them to each other. And as a result of that, now you have these sort of bundles of RAM and disk, things to store things on in various ways. So a rack might have 80 servers on it. So then you've got something like a terabyte of RAM. Your access times have dropped significantly, get quite a bit slower since you're now bound by the network speed. So now instead of 100 nanoseconds, you're talking about 300 microseconds. So you've lost several orders of magnitude there. You've also lost quite a bit of throughput, 100 megabytes a second. So as you get these bigger and bigger accumulations of resources, you get slower and slower access. Similarly, your disk, you're getting 80 times the disk. Your seek time hardly goes up at all because the network overhead isn't very significant there, and your throughput doesn't actually drop that much either because the network is almost as fast as the SATA bus. And then finally, you get a bunch of racks, you put them all together, and you make a cluster essentially. And a cluster, is going to have 30 or more racks. And now you're getting very large pools of resources. Right now you have maybe 30 terabytes of RAM available to you, and maybe 5 petabytes or something like that worth of disk, or approaching that, which is great. And once again, on the disk side, the key sort of thing that happens here is that these cluster switches are much lower bandwidth than, or at least dedicated bandwidth between machines than we get out of the rack switches on individual machines where we have true, that are not oversubscribed at all. So as a result of that, you start to lose significant throughput. So you're down to 10 megabytes a second worth of throughput between any given machine. And so your access to this shared pool of resources is quite low in terms of throughput, although you don't give up a huge amount in terms of additional latency by adding this additional layer on top. So depending on what you are doing, thinking about whether to think about things on the machine level or on the rack level or on the cluster level it may be that you need to do things, you need really, really fast access, you need to do really immediate computations or something like that, something like web search, where you have just, maybe 100 milliseconds or something like that in order to do vast amounts of computation. Most of that heavy lifting needs to be done on local machines, and then with some communication between them, obviously, as you get to your results. But other things, in terms of, I want to generate a bunch of, a huge amount of data, I want to generate a bunch of map tiles or something like that, that they're giving up a few milliseconds of latency isn't that important, and instead you want to have the huge amount of resources available in terms of storage and so on. So just an important way to think about how to access your resources. And now I'm going to move on to talking about reliability and availability. So one of the key things I think to realize is as you start to move towards scale, and really any time, as long as you're not basically fooling yourself, is you have to deal with the fact that things are going to crash. Even if you get the most reliable servers in the world, and you're talking about like something with an MTBF of 30 years, right? Like you could get a server, you could start it, and you could use it heavily, and it wouldn't break for 30 years on average, right? That would be an incredibly reliable server, vastly more reliable than most of the hardware that we're used to working with. Even if you had a data center full of these things, if you built a computing system with 10,000 of them, every day one of them would break, right? Even with the most reliable hardware in the world. So as you start to get towards large scale, it becomes an inevitability that you'll have a constant stream of failures. And that means that you need to design your software in order to deal with this. So the 30-year MTBF is crazy. The next sort of 2 slides will demonstrate this. First, if you look at a typical sort of level of flakiness, it's more like 1 to 5% of your disk drives are going to break in a year, not 30 years between failures. And servers are going to crash twice and maybe not come back from it. So huge failure rates that you need to make sure the software is capable of dealing with. I'm not going to read through all these. You can read them yourself. These are, in our experience, the sorts of things that you run into in the first year after you turn up a new cluster. So all sorts of, wow, you can't read the bottom of that, that's sad. All sorts of stuff that's going to break your service, basically, if you're not resilient to various sorts of hardware failures. Some of these are relatively minor. You get plenty of warning with them, like these rack moves, but they still take servers down for 6 hours at a time. Some of them, are totally spontaneous. A PDU failure, if you lose some of your power infrastructure, you're going to lose a bunch of servers all at once instantaneously with no warning, and you just have to deal with it. So the way this fits together in Google's cluster environment is essentially you've got thousands of machines. Typically, sometimes you might only have one configuration, but sometimes the cluster might have been built up over time, and so you might have 3 generations of hardware or something like that, all in one place, which is a management challenge of its own right. Underlying all of that is some storage and some scheduling infrastructure for your compute resources. So you have a place to store all of your information, and then you have a way to submit jobs to this scheduling infrastructure that's going to run it for you when resources are available. And typically, there are a lot of people trying to run jobs all at once. And we'll get to some of the reasons why that's the case in just a minute, but there's hundreds or thousands of active jobs. Some of what we call a job is only one task running on one particular machine, but another job, one of the technologies that we came out and talked about very early on in our development was MapReduce. And a MapReduce might be running on 500 machines or something like that. So that's sort of one job, but it's got 500 different servers running it simultaneously. The other complication in all of this is that some of the tasks are sort of batch oriented, some of them are low latency oriented, and have user facing jobs, and they have very different performance characteristics in terms of what we're trying to optimize for. So most of what we do at Google is distributed systems. So, and this is largely because almost all the problems that are interesting to solve are too large for a single machine, right? Like you can't do web search on a single machine because the whole web doesn't fit on a single machine. Sort of makes sense. So therefore, you have to think very carefully about things like, how do I split up my data in order to be able to access it efficiently? That means you need to have high capacity systems even in a single data center. You're also going to need to distribute, in order to have reasonable latency for users all around the world, you're going to need to have your service distributed to various different places all over the world, right? Like if we only ran web search in New York City, that would be great for people that lived on the East Coast of the United States. It would be okay for people that lived in the rest of the United States and Europe. It would start to not be very good for people that lived in South America or Australia, and it would probably be really bad for people who lived in India, right? So in order to improve on that, we want to place data centers and data in places all over the world. So that means, once again, the system has to distribute well in order to make that work. And the other approach that we take, which I'll get to in just a second, is that the services, even internally, we have a bunch of different services and things talking to each other. A single web search touches 50 different sets of services or software stacks of their own on thousands of machines, all of which are providing a little bit of assistance in order to make the query go correctly. So this notion of having many internal services is driven by the fact that it's simpler from a software design perspective to have relatively discrete services with simple interfaces that are clearly defined using a mechanism we use called protocol buffers, which we'll talk about in just a second, and is one of the open source tie-ins here. Secondly, that if you have relatively small services, it's easy to do testing on them, right? When you do regression testing and so on, you only have to test a small number of interfaces instead of testing your entire system at all the places you can do, and you can run lots of experiments. The other important thing is you can decouple things, right? Like if the part of the system that knows about, say, weather is decoupled from the part of search that knows about, spelling or something like that, you can update them at different speeds, right? Like the weather stuff the weather stuff may only need to get updated once every 6 months, the way we handle it. Obviously the weather changes every day, but the spelling models may be more dynamic and get updated more frequently, or vice versa. And also, it's easier to organize around small teams, right? Like if you have a project where you have a project that's just called web search and everyone has to work on it at the same time, that's a huge management challenge, and project management challenge in particular. Whereas if you have these smaller components, you can work in sort of a sane size development team of maybe 8 people or 10 people or 20 people. So one of the things I just mentioned in terms of how the software interacts is protocol buffers. I'm not going to spend very much time here because we don't have a lot of time. This has been open source, but basically it is a mechanism to allow for self-describing ways to interact between services with multiple languages support, and it has to be really, really efficient. So here's an example protobuf which lost its formatting somehow, but basically just a series of types. We have something called estimated results, which is an int that's required as part of a search result, and then we also might have an error message that's optional, it's a string, and then we'd have this group of things that are the actual results with scores and document IDs and some details about them that we'll get one or more of. And that's a human can look at this and sort of understand what the API is going to look like as a result, which is nice. The nice thing about, so to that point, they're automatically generated language wrappers, and one nice thing about them is that if the system doesn't understand parts of it, they just ignore them but pass them through. So if you have 2 systems talking to each other, but there's intermediates that they have to go through, you don't have to upgrade everything along the path when you upgrade the endpoints, which is nice. Has to be super fast, since this is our primary way of having services talk to each other. And you can also use it to do service specifications. This is, if you're really interested in learning more about this, you can go to code.google.com/p/protobuf. All right, on to storage. So our storage infrastructure at Google is big. This is a little bit out of date. This talks about GFS. We're actually in the process of migrating to what some people call GFS v2, or is called Colossus within the company, which is a new instance of the Google storage platform. But sort of think of it as there's over 200 sort of GFS clusters. Some of these clusters have thousands of machines in them, And so we looked earlier when we saw the math on how much space that talked about. So often petabytes of space. As we see here, there's file systems over 4 petabytes. And in individual clusters, you'll see 40 gigabytes per second of read and write load against an individual cluster's worth of storage. So huge pools of storage accessed by thousands of clients. So these are huge shared resources, essentially, where we spend a lot of, where there's lots of storage and lots of I/O, all in the presence of lots of hardware failures. More recently than GFS, we've added a new system that's a little bit more structured. GFS essentially provides file system semantics. Bigtable's a newer system that we started working on in 2004, and it provides sort of more database-like semantics. They're more structured. I could spend a little bit of time talking about this, but once again, we don't have that much time, so I won't. But Bigtable is now used by a bunch of Google services. This lists a few of them. Certainly App Engine and Google Storage for Developers, which are, once again, our 2 cloud offerings, also use it on the back end. There's over 500 separate instantiations of the Bigtable service. And the largest one of them is over 70 petabytes in one single storage instance. That one also is the champion for I/O, does 10 million ops per second and over 30 gigabytes a second of I/O. So this leads us to 2 challenges, right? One of the things I just mentioned is that there's often thousands of users competing for the same storage space. So one of the challenges that we face there as the people that run this service is how do we get users isolated from one another such that they don't cause interference, right? Like if we were just to, if we didn't have good user isolation, a service like web search or something like that wouldn't be able to use the same storage that something supporting like a big batch MapReduce or something would be using, because the MapReduce might totally overwhelm with huge volume the relatively small but latency sensitive queries that the web search has to do. Yes. See, it's good I'm going fast. All right, so in order to do this, we start off by dividing the classes into 3 categories, essentially. First is things that are low latency. These are things that need access to resources essentially right now. So something like serving map tiles would be a good example of that, right? Like if you go to Google Maps and you have to wait 5 seconds in order for one of the tiles to load, that's really annoying, and you might just go away and use Bing instead. But if we can get the map tiles to you really fast, then you'll realize how awesome Google Maps is and you'll keep using it. So we want to make sure that some of these things have very fast access to this. Then there's other things like instead of serving map tiles, if we want to generate them, lay down all the roads and all the information that we have about the maps, that needs a lot of throughput over time, but it doesn't necessarily need, a 5-second delay for that is not going to make a big deal as long as the whole task completes in 6 hours or something. And then lastly, we have this class of things that we'll call best effort, and these are things that can tolerate long delays. They're not that important. Oops. And these would be like experiments or one-off jobs that people might be running just to sort of try something out or do a one-time analysis of some sort. So getting this, that's exciting over there. Getting this done is a mix of tools in the kernel, which we rely heavily on for open source, versus some stuff that we've done ourselves in user space. And basically the way I would describe this as breaking down is the kernel works really well for solutions that are oriented around a single machine, right? Like if we want to say like user X can have no more than 5% of the disk time on this particular machine, or that user gets to go to the head of the line in order to get access to resources on this disk, the Linux kernel provides a really rich set of tools and getting increasingly rich as time goes by in order to do that. On the other hand, if you want to do things on a cluster level, if you want to say something like user X gets 5% of disk time across the entire cluster, or something like prioritizing low latency users ahead of batch users in terms of scheduling over a longer period, that needs to be done at that tends to be done in user space, because the set of tools in the kernel are obviously geared towards one particular machine. So the key kernel tools that we use, and these are not just strictly limited to storage, but basically there's a use of fake NUMA nodes in order to provide memory isolation. We use CPU limits and the completely fair scheduler in order to try to provide relatively good, strong CPU isolation. And then the Linux I/O scheduler has really done a tremendous amount of development recently to allow us to help prioritize and constrain the amount of disk time that any given user's allowed to have. The other challenge I'll mention really briefly before we run out of time is system management. There are literally, as I mentioned before, thousands of servers per clusters. There's many of these clusters. Software changes essentially all the time. Some of our software packages get released as often as once a week. And in between that, there's often, configuration changes that are required as well. Once again, here I would characterize it as there's lots of really good open source tools to manage things on a machine level. SSH, package management, and so on. There's starting to be tools to manage things on a cluster basis, but they tend to not quite match our environment. So we have mostly purpose-built our tools for cluster level management. That means mostly a lot of Python code that various folks in SRE and other parts of the organization have done. So one example of this is like, how do you do software upgrades, right? It's a tremendously complicated process when you've got thousands of servers times potentially a lot of different locations. And so step one is you need to sort of what we call canary test the software to make sure that it's not going to break when we get it out to production. So first you have to upgrade a single binary on a single machine, see if that breaks. Then, assuming that works, you upgrade all the rest of the machines in that cluster. Watch and see if anything bad happens there before you go on and upgrade the rest of the world. Assuming that goes well, then roll out the process to the rest of the world. Which is all fine. A human could do that as well, but once we're talking about thousands of servers in lots of different locations, then you need that all to be automated, so all that logic has to be implemented. Similarly, you need to be able to control the rate of upgrade, right? Like how many servers can be down at once? If you think about this in the context of storage, how much of your I/O throughput are you willing to give out? Or how many instances of any given piece of data, even if it's stored redundantly, we can't have all the copies of it unavailable all at the same time. So we need to be careful about which servers are getting upgraded in which order. And then it may be the case that you don't want to upgrade more than one cluster at once, because people may be depending on having no more than one of them down in order to make sure their service is reliable. And similarly, you may not want to do something as critical as the underlying storage infrastructure. You may not want to upgrade too fast overall. You may not want to upgrade it all in a day. You may want to give yourself 2 weeks to slowly roll it out to make sure nothing unexpected happens. So similarly, you need to be able to, in the midst of this process, you need to be able to pause or roll or resume that pause or roll the whole thing back. And you need an automated framework around all this stuff. And this is a really hard problem space, and one that I'm not going to say that we've really licked. We have a lot of custom tools, all to do very similar things, and none of them really quite work right. So I think this is a great area. I mean, in many ways, this is some place where every different organization is going to have a lot of custom requirements, but it's also a great area where there's opportunity for open source, because I think it's a problem space that as entities grow, almost every entity is going to face having to deal with, and there's not a great tool set around it today. And with that, I'm done. I think I'm time, unless I have time for questions and people have it. Yeah, I don't know. Am I getting kicked off now? Yeah, okay. Thanks.